It's a pleasure to introduce Gilles Brassard, who is one of somebody who's made such important contributions to quantum information science. It's terrific to have him here today, and he's going to speak about information in sequence.
Thank you very much. All right. So this talk, of course, is in honor of Jeff and his bananas. So let me start with a few recollections. The first time I met Jeff was last century when he invited me to give a talk on quantum teleportation in 1999. It's not written here, but that's what it was, at his weekly seminar. So already in last century, he had a weekly seminar on quantum information and quantum computation. That's pretty good. 1 year later, he came to a Quantum Foundations in the Light of Quantum Information workshop that I organized in Montreal, which he mentioned yesterday in his talk. And so this workshop took place in May 2000. And here's my earliest picture of Jeff. In fact, this was a group picture. It was a small meeting. And here's Jeff. He hasn't changed much. Rediger has changed quite a bit more, I would say. And as for me, well, my hair was somewhat darker, and I had a beard. But as you see, I had the same T-shirt. Right here. Okay. So at that meeting, so we're talking about the year 2000. At that meeting, that was the program, and Jeff talked about some reflections on quantum logic, whereas I talked about quantum information in the light of quantum cryptography. Remember, the meeting's theme was quantum foundations in the light of quantum information. And I should have said this was co-organized by Chris Fuchs. I can't resist spending a few minutes on the talk I gave back then. In particular because Jeff mentioned it yesterday in his own talk. So in that talk, the idea, I asked the following question. I asked, is it possible, this was just a dream, somewhat a silly dream, is it possible that we know as a theorem that perfect confidentiality is possible? That's quantum cryptography, quantum key distribution. At least in principle, we can have unconditionally perfect confidentiality in the transmission of information. We also know as a theorem of standard quantum mechanics that it's not possible to have perfect bit commitment. And if you don't know what that is, it's not really important for this talk. But bit commitment is impossible, whereas confidentiality is possible. And the question I asked back in 2000 is it possible that from only these two things, which instead of calling theorems, we could call axioms, is it possible that from these two axioms, one could rederive all of quantum mechanics? And I didn't believe it was possible, but I just, as half a joke and half a challenge, I proposed that. And again, I was not really serious. And in particular, shortly thereafter, John Smolin proved that it's impossible. Nevertheless, Jeff is probably the only person who took me seriously. Sorry. Let me just explain what I, graphically, excuse me, what I mean by this dream. So here's what happened really in this joke. I insist, please do not take this at face value. This is not meant seriously. But I think it's nevertheless a nice illustration of the thought process. So at some point in the past, God created Bob. And he asked Bob, hey, Bob, what do you want? And Bob said, oh, God, I'd like confidentiality. It's kind of a silly thing to ask because he was all alone by that time. So God said, let there be confidentiality. And he thought it was good. So then God created Alice. Eve came later, actually. So, and God asked Alice, what do you want? And as you might expect, she said, oh, I want commitment. And so God said, let there be commitment. And then all hell broke loose for some reason. So God realized that it's not good to have confidentiality and commitment, and therefore he needed to figure out a way to provide confidentiality to his creatures, but not commitment. And that's when, well, he had no choice. He had to invent quantum mechanics. And so again, the idea is it possible? Now, let's be serious. One last thing before being serious. He had to invent quantum mechanics, but by that time it was too late. So, so back to being serious. So the question I asked is, can we base quantum mechanics on information-theoretic principles? And if so, which ones? And as a joke, I propose conventionality and no commitment. So Jeff wrote this really influential paper with Rob Clifton and Hans Haverson, in which he essentially followed my order and provided something which was not quite what I asked, because what I asked was impossible. But still, he based some aspects of quantum mechanics, some kinematic aspects, on information questions like no-bit commitment. To my great surprise, he did use that. And instead of confidentiality, he used no instantaneous signaling, no cloning, or no broadcasting, to be technically more precise. And again, this was suggested to him by this meeting back in 2000. But also, as Jeff mentioned yesterday, since then he's had second thought about his whole project, because he needed to assume a C-star algebra structure to the universe, which, as he said, is very close to just postulating quantum mechanics in the first place. So that's what I meant back then by information and quantum mechanics. And I gave a talk on this at the first QPON conference in Vienna. That was for the 60th anniversary of Anton Zeilinger. And after my talk, I was approached by the editor, or one editor of Nature Physics. Nature Physics does not quite exist yet, but he asked me to write the opening commentary in volume 1, number 1, page 2. That's why I have the opening commentary of Nature Physics, is information the key? Asking the question. Where I asked, do the truly fundamental laws of nature concern not waves and particles, but information? And, well, let's be honest, someone had asked the same question before me. Wheeler, back in the 70s, Wheeler would ask his best students to derive quantum theory from information theory. So this talk is, yes, information is the key. Now, some people have worked on my original project, I should say on Wheeler's project, after Jeff, and again to base quantum information on something else than the usual axioms, in particular Lucian, although that was back in 2001, so it was really early. But Lucian's purpose was not to base quantum theory on information. He just wanted different types of axioms. And then later, in 2011, I think, Messanus and Müller had something which was much more using information. So they derive quantum mechanics from 5 simple physical requirements based on assumption regarding preparation, transformation, measurement, which is kind of information. And then the answer, it was squarely answered by Kerbella and co-workers who really based quantum theory on information. Good. Now, let me switch gears and ask again something which has to do with information and quantum theory. But now let me ask, what information? What is the information that is central to quantum theory? And this is joint work with Paul-Raymond Robichaud, who is sitting here. And let me start, since this is somewhat a philosophy conference, with a Plato and Kant view of the world. I'm not a philosopher, so if I say nonsense, please be indulgent. And in particular, they postulate a noumenal world. And the noumenal world is really all there is. And because Kant is German, he also said that, which I won't try to pronounce. And so the noumenal world is, in a sense, the real world. That's what really is. And there's nothing else. And then, so for Kant, it may exist, that's not clear, but it's completely unknowable through human sensation, which does not mean unknowable through human thought. Or at least we can postulate about it. So there's the noumenal world at the top, and then there's a phenomenal world, which is the world of our sensations. It's what can be apprehended. And I'm going to be somewhat more generous. In the noumenal world, in the phenomenal world, it's all that can be apprehended with unlimited technology. We don't need to see it with our naked eyes. Any technology is allowed. But at the end, it's something that we must apprehend ourselves through technology. Well, and I say unlimited, but of course I mean limited by the laws of physics, but no other limitation, no technological limitation. And the main postulate here is that both the noumenal world and the phenomenal world can be described in terms of information, and that there is a function, a mapping, that goes from one to the other. This mapping is epimorphism, so let me explain what this means. Epi means that it's unto, which means that every phenomenal state has at least one noumenal state that is mapped to it, which is, all this means is that there are nothing that can be apprehended that does not actually exist. That's all it means. And the morphism part of it is some algebraic structure which will preserve all the desired properties. And let me not try to be more precise about it now. However, one thing that we will show is that this epimorphism cannot be one-to-one, meaning that it has to be, again, any phenomenal state comes from at least one noumenal state, but it will not be the case that there's a single, it's not a bijection. There will be many different noumenal states that lead to the same phenomenal state, and that's unavoidable. Now, people in quantum information usually use the word ontic for what I call noumenal. So you might wonder why I changed the word. Well, I used an older word, in a sense. It's been around since Plato, in Greek, of course. But that's not why I changed it. I'm not proposing to change. All these people have been talking about ontic states and all that for years and years, and here I come. No, ontic is no good because Plato came before you. No, that's not the idea. The idea is that, in fact, what I call noumenal and ontic, what others call ontic, is the same. However, the reason for changing the word here is that the ontic state has been systematically compared to the epistemic state. And this is definitely not epistemic. It's different. So since I have to change this one, it's better to change that one as well to avoid confusion. And it's not the doxastic state either. Now, I remind you from yesterday, the epistemic state is a state of knowledge. The doxastic state is a state of belief. The phenomenal state is all that is knowable through perceptions, through all that can be apprehended. The big difference is that the noumenal state includes everything that could be apprehended or learned, whereas the epistemic state is what is actually has been learned. So it's not so the phenomenal is not a state of knowledge, a state of potential knowledge. We could say it that way. Okay. So that was so far I talked about the state of the world. Now let's talk about systems. I don't want to try to define formally what a system is. It's in fact more complicated than one meets the eye. But for this talk, naively, it's enough to think of a system being either one particle, one observer, one something that you want to study. And whereas so far I talked about the entire world, we want to talk about the state of a system, not just the whole world. And so we will have noumenal states and phenomenal states for systems. And now systems can evolve. So we have, let's say if we have a state at time t0, we can apply some operation. In quantum mechanics, be it unitary U or Hamiltonian H. So we apply some operation to the state, and this results in a new noumenal state. So that's what happens in reality. Now the new nominal state gives rise to a phenomenal state by the same mapping. And what I want to stress is that we cannot manipulate at a phenomenal level. We can only manipulate at a noumenal level. But, and this is what's called epiphenomenalism. But of course, this operation is reflected in the phenomenal, at the phenomenal level. And the fact that this is possible and well-defined comes with phi itself being a morphism. So we have to do that right. It's not, that part is not difficult. So it's well-defined. I use the same symbol because in terms of what we call in algebra an action, it's the same. It could be a group. It doesn't have to be a group underneath, but if it's a group, we call it a group action. And is the same group element. U will be the same group element acting differently on noumenal and phenomenal states. So it's the same U as an action, the same U as a group element, but the action is different depending on what level it acts. All right. Now this diagram commutes. Let me explain just what it means. When I say that diagram commutes, it means that you can follow the arrows one way or the other, and you get the same answer. So that phi of U of whatever the state is the same as U of phi of the same initial state. All right. Now, let's talk about system A. Instead of writing noumenal state, which takes a lot of space every time, I'm going to denote the noumenal states by M. So that's the noumenal state for system A at time 0. And Ym doesn't really matter. However, for the phenomenal state, I remind you this is what can be apprehended. So there's an obvious choice of notation for the noumenal states, which is rho. All right. Now, a system can be split, which means that if I have a system AB, which is composed of 2 parts, I can split it into the A and B parts. And this is done mathematically by a projection operator. Now, in physics, it's more useful. It's more usual to see that we trace out B to keep A. In mathematics, it's much more natural to project into A. So think of pi A as the same as tracing out B. And I can trace out A as well, and therefore project them to B. So this AB system is split between A and B. And then this gives rise to, so this is at a noumenal level. You do that at a noumenal level, and gives rise at the phenomenal level to the corresponding states, not of knowledge, but of knowledgeable, the things that could be apprehended. And it turns out that, again, these projections on the noumenal states, you can also have projections on the phenomenal states. It's not the same function, formally speaking, but it's natural to use the same symbol. And the thing that happened, not surprisingly, is that this diagram commutes. Meaning that if you start from a noumenal state, a composite noumenal state, and you take the A part of it and look what could be apprehended about that, it's the same thing as if you look at what could be apprehended on the AB part, but only look at the A part. So this thing commutes, and that thing commutes as well. There's nothing surprising yet. Now things are going to start being different from what you've learned. Until now, there's really, I mean, you're probably bored to death. Now things will start being different now. You can take two systems at a noumenal level and join them to produce what we call a joint product. And this joint product will be the same as the combined system. If now we look at the phenomenal version of that joint system and compare it to the phenomenal version of the split system, well, now it is not possible to join them. You cannot join phenomenal systems or phenomenal states, whereas you can join noumenal states. And the fact that this is not possible is very well known in standard quantum physics. Because if you think of that as a density matrix, you all know that from a density, if AB is entangled, and you look at a density matrix that describes A and the one that describes B, from them together you cannot define uniquely the density matrix for the AB system. So the fact that this is impossible, whereas this is possible, is the reason why we need nominal states. In standard quantum mechanics, we work almost exclusively at the phenomenal level. And this makes it impossible to join two systems. And that's why we have all these statements that the whole is more than the sum of the parts. If you know everything that you could know about A and about B, then you don't know everything you could know about AB. Well, this is true at the phenomenal level, but not at the noumenal level. And now we have this join requirement, which essentially says that it all works out. Namely, if you take a composite system and you split it, and then you recombine it, well, you get what you started from. Again, this is entirely impossible in standard quantum mechanics. And if you think that I don't know what I'm talking about because I claim this is possible, just please give me benefit of the doubt for another 15 minutes. All right. And I stress that this is true even if A and B are entangled. We can also evolve separately a composite system. So if I have an AB system at time 0, I could split it now at a noumenal level. But split at a noumenal level really means I physically take the physical system in two parts and move them apart. There's no operation other than moving them apart that you need to do here. It's done by nature, by itself. And then I could evolve both subsystems. I apply U to A and V to B. And then I could combine them again. And I will get the joint system of A being, A being evolved by U and B being evolved by V. Instead, I could have done something else. This is the counterfactual. So I cannot do both. But instead of doing all the black stuff, I could do the blue stuff, which is apply U tensor V to the AB system. And I didn't write the usual tensor symbol because this is more general than quantum mechanics. It's a direct product in the algebra that's underneath. If we were doing quantum mechanics, it would be the tensor product. And you've guessed it, of course. Whether you do this, whether you evolve the AB system under U tensor V, or you split them, evolve A under U, evolve B under V, and then bring them together again, well, you get the same thing. So separate evolution is essential here. And now we come to no signaling. What does no signaling mean? No signaling is something which is at the phenomenal level. No signaling essentially says that no matter what I do, if I have an AB system which is could be entangled, but it's split between Alice and Bob, there's nothing that Alice can do that will signal anything to Bob. Again, that's a phenomenal statement, not a noumenal statement. And so what it means is that no matter what Alice and Bob do to their systems, if U to A and V to B, if instead they do it separately, so if instead of doing UV to AB, Alice does U to A and Bob does V to B, then, I'm sorry, I only have Alice here for simplicity. If Alice does U to her system, what she gets here will be the same state, regardless of what Bob could have done. That's what you should understand here. This is true for all V, meaning no matter what Bob does, what Alice gets after having done U to her part is the same. It commutes. So this is, after Alice has done U to her system, what she has is the same as if Bob had done anything at all in addition to Alice doing U. So this says that Bob cannot signal to Alice. And again, this is a statement which is purely at a phenomenal level, and it's perfectly well established in quantum theory and standard quantum theory. However, my claim is that we can lift this statement at the noumenal level, and that's not standard at all. So if we replace here we had the phenomenal state, a rho, we replace it by the noumenal state, and we do the same, and so we apply U tensor V to the AB system. If we also do it so this is if both Alice and Bob do something. If only Alice does it, then again it commutes. So this is not no signaling. This is much stronger than no signaling. This is locality. In fact, it's local realism because the noumenal aspect is realism. But what I just added here is the locality aspect of it. So a local realistic model of a theory doesn't have to be quantum theory, of a physical theory. A local realistic interpretation is given by defining the noumenal level and having this diagram commute. That if Alice does anything she wants, U in this case, to her system, then what she has after that is the same. Not only what she can apprehend or measure about it, what she really has is the same after she's done U to her system as if Alice and Bob had done U and V respectively, the same U, but Bob had done anything he wants, and then we look again at what's in Alice's hand. So this is much stronger than no signaling. And here are two theorems. The whole point of this talk are these two theorems. Theorem number one, not surprisingly, any local realistic theory is non-signaling. So if this AB system is split between Alice and Bob, and if it's local realistic means that if Alice does something, then her part of the system, system A, will evolve to what it was, something else. And local realistic really means that it doesn't matter what Bob does on his side. What's in Alice's hand remains the same, no matter what Bob will do. That's what local realistic means. And therefore, it's not surprising that anything that can be apprehended by Alice is the same as well. So this is not at all a surprising statement, but it deserves a proof. And I'm not going to go through the proof. I just want to show you there is a proof. It's just plain math. It's reasonably simple, and it's completely formal. But this here, I'm not going to go through the proof, but just a statement, really. This means that the phenomenal state for Alice and Bob combined, if you evolve it and look at what Alice has, does the same thing as if you take the same nominal state initially, look only at what Alice has, and Alice evolves it. And this is true for all V, that's the point. All U and V, but particularly no matter what Bob does with V, this is the same as that. And this means non-signaling, again. So this is not surprising. Where it gets more interesting is the converse, that non-signaling theories are local realistic. And, well, this is actually, the proof would be a bit longer. Actually, no, the proof would be much shorter because that's nonsense. That's nonsense, but not for the reason you think. That's nonsense because standard quantum mechanics is non-signaling. We all agree on that. But again, standard quantum mechanics is certainly not local realistic in the definition I gave of local realistic. So this is not true. So we have to try again. Let's change the statement of theorem 2. Non-signaling theories can be made local realistic, which means that if you have for any phenomenal level, define any physical theory which at the phenomenal level is non-signaling, then you can derive a noumenal, you can lift it at a noumenal level, which is local realistic. And the way that it's done with standard quantum theory does not work. You have to do it a different way. But because quantum theory, well, that's right. So yeah, you get a complete choice of the noumenal states to do that. But the theorem is that you can always do it. And this includes quantum mechanics, because quantum mechanics is a non-signaling theory. Therefore, it is local realistically noumenable, whatever. It also includes banana world. Banana world is obviously non-signaling, therefore it can be made local realistic. And in fact, this is much, much easier. And this entire line of work started with a local realistic version of the banana world. That was even before Jeff thought of bananas, because of course it was done with non-local boxes, PR boxes. I have to make a small disclaimer. There are technical caveats. This theorem, the way I wrote it is all encompassing. We don't know that yet for sure. That is true for all possible non-signaling theories at the phenomenal level. But if the algebraic structure, which is underneath, that drives the thing, that drives the phenomenal states, has a group structure, which is the case for quantum theory, which is the case for non-local boxes. If the underlying algebraic structure, which makes the actions, so if you have group actions, then we have this theorem. And it might be true in all cases, but we don't have it yet. But all useful cases will be covered, probably. Okay. Now, at this point, if you're still paying attention because I've been saying such crazy things, you're probably thinking, oh, you mean this guy has not heard of Bell's theorem? Because it looks like Bell's theorem proved that this is not possible. So let's see what Bell said. It's impossible for nature to be local realistic. Bell said that. However, he did not, well, maybe not in these words, but of course it's assuming that quantum mechanics predictions hold true. So under the assumption that quantum mechanics is correct at the phenomenal level, essentially, that's what it means, then it's impossible for nature to be local realistic. I want to stress that, again, this is not a quote. The actual quote would not have the word impossible, but I needed to have it for what's coming next. So it's not a quote, but it's the spirit of what he wrote. I want to stress he did not write that in his famous 1964 paper. That was much later in the Nouvelle Cuisine paper in 1990, I think. His very, very last paper. That's where he made this fatal mistake. In the original 1964 paper, he did not say that. Well, now, the really, I think, really funny thing, and the reason why I wanted to have the word impossible in Bell's pseudo-quote, is that the same John Bell also said, of course, we know since last talk that we don't have to worry about that anymore. It does work out at the phenomenal level. Every indication is that indeed quantum theory at the phenomenal level works, and therefore we don't need to add these caveats. All right, so the same John Bell also said, what is proved by impossibility proof is a lack of imagination. Coming from a man whose main claim to fame is is an impossibility proof, that's a really bold statement to make. But he said both things. So let's refer to someone else. Einstein said, imagination is more important than knowledge. So the whole point here is can we make things work? Can we get this theorem number 2 just by using a little more imagination? And in fact, what Bell actually proved in his 1964 paper is not this. It's not Bell's original paper, 1964, is not about nature being local realistic or not. It's about local hidden variables. So Bell's theorem is about the impossibility of local hidden variables to explain quantum at a phenomenal level. And that is absolutely correct. And that's what he did in the 1964 paper. So I have no issue against his 1964 paper. But it's different. It's entirely different to talk about local realism and hidden local variables. Any hidden local variable theory will be local realistic. But it is possible to be local realistic in a different way by using more imagination. So is there a local realistic way to do this theorem 2, which could rise any non-signaling theory at the phenomenal level to a local realistic theory at the noumenal level? Well, actually, there are 2 key ideas to make it work. One is to acknowledge that the reason why we believe in all this stuff is because of the experiments. Thanks again for the last talk and all the work behind it. However, all of these Bell inequality experiments, they have one more loophole than, probably more than one more, but one loophole that was not mentioned in the last talk. And in my view, it's not a loophole because a loophole is somewhat negative. Loophole is something you want to avoid. In fact, the loophole in question is something I believe in, which is that, so Alice and Bob, they are separated. They make their measurements. And then the outcome of the measurements, given the inputs, is just, that doesn't seem to be possible in the classical theory. Statistics just don't work. Something's wrong. Well, you violate Bell's inequality, right? So we can violate Bell's inequality by having Alice and Bob being space-like separated, because you want to close the locality loophole. So Alice and Bob are space-like separated, and they make these measurements, and they violate Bell's inequality. No, they don't. Bell's inequality is not violated when Alice and Bob make their measurements. Bell's inequality is violated when the data is brought back together for comparison, for analysis. So it's not at the time that the measurements are made that Bell's inequality is violated. It's only when the data is compared. And to compare the data, you need to bring it together. And that cannot be done faster than light. So that's the first key thing to realize. That you cannot violate Bell's inequality faster than light, even if you think that you're space-like separated. In principle, it's impossible. All right, so now you might think, and it would be a reasonable thing to think, well, but when you get together and compare the results, these results were already decided out there. So what difference does it make to compare them when you can, because they're back together, versus counterfactually claiming that this was also that this violation was already there before comparison. So it's and the only way out of that is to reject that measurement outcomes become definite. So indeed, I agree that if you think that when Alice and Bob make their measurements, it's set in stone, then, and this happens in space-like separated fashion, then it's not by bringing them back together at the slowest of light that it will change. So if Bell's inequality are violated here, they were back there as well. And now Bell's theorem applies and everything is non-local and whatever you want. So, but if you accept that measurement outcomes do not become definite, they're not definite when measurement is made out there, then there's at least a hope to get a noumenal theory that will be local realistic. So you need to accept these two things. Well, this is nothing you need to accept. This is a fact. And you need to accept this possibility, and only that. Everything else would be math. Okay. This is how to do it in the banana world. Well, Jeff missed that. So non-local boxes, we're going to change it with banana world. And I'm going to go through this if you ask me the question during question period. So the talk is almost finished, but I want to mention that almost essentially everything I've said is not new. There were precursors who had enough imagination, not Bell. Of course, Everett, because the idea that the measurement is not, that the outcome is not definite, it's not because it's going to change as they come together. That might be a way to do it as well, but I don't like the idea. The way that we're going to have these measurements not being definite is because in the case, for simplicity of a binary measurement, the two outcomes do occur simultaneously. It's not one or the other, it's both of them. So this has a many-world flavor. But it's not a many-world. You can do that locally. Both measurements occur here. You don't need the whole universe to split for that. So it's kind of a localized version of many-world, and we call it parallel lives. Alice and Bob, when they make this measurement, without knowing so, will start living parallel lives. And when they meet, it's when they meet that the interaction will occur, that all the magic of quantum mechanics will occur. And again, I can explain how to do that with the banana world, if you ask me. Frank Tipler might have been the first person to realize things similar to what I explained. Because as far as I understand, Everett had, despite his immense contribution, in Everett's mind, in Everett's version of what he called the relative state of quantum mechanics, that was not a local theory. Not local in the sense of at the noumenal level. Frank Tipler found a way to do that. I think he was probably the first person. And he explained his ideas to David Deutsch. And Deutsch and Hayden published, giving full credit to Tipler, of course, published a paper on the archive and also in Royal Society something in 2000, which does essentially what I explained, at least for quantum mechanics. What I explained works for any, or with a caveat, any any theory which is non-signaling at a phenomenal level, not just quantum theory. Darsh and Hayden did it for quantum theory, but in the paper it's not very easy to read. It's a bit I would say a bit obscure, and also Colin Bruce. Colin Bruce is Colin Jack's pen name, actually. He wrote this really nice little book, Schrodinger's Rabbits. It's a popular science book. And here, in this book, he describes with extreme lucidity the idea of parallel lives. We didn't know about it. Once I gave a talk about this in Oxford, and Bruce was there, I should say Colin was there, and he gave me his book, and wow, it was there already. So what did we do after all? Looks like, well, we're too late. We did make it simpler. We also have a complete generalization, as I said, which I forgot to write here, complete generalization to any non-signaling phenomenal theory. We also have a proof that this idea is not the usual Everettian approach. And in particular, I think, I don't want to insult anyone, but I think that most Everettians take it for granted that a wave function of the universe is a complete description of the universe with all its massive superposition. But that's not true. We have a theorem that this is not possible. If we want to make quantum theory local realistic at the noumenal level, it cannot be that the state of the universe is a wave function of the usual quantum mechanics version. All right, so now I'll stop for questions, but let me feed you some. You might want to know how we do Banana World, because that's the easiest way to do it, and it's really entertaining. You might want to know how to do the whole of quantum mechanics, which would take a few more hours. But I can zip through slides if you ask me. And that a wave function cannot be a full description of physical reality. So I have slides for all of these things. And of course, you're entirely welcome to ask any other question. All right, thank you. And also, I have some number of copies of a poster, two-sided poster. On one side, the Banana World, aka non-local box, explain science fiction story. The other side is the math for quantum mechanics. All right. Yeah.
So I wonder if you have a world like the one you described with these two.
Speak out, please, as I will always say. Yeah. Go ahead. No, start again and speak out.
Pardon?
Start again and speak out.
Okay, so suppose we have a world of the kind you described with these two key features.
Yes.
And then basically what you're showing is that if you would be part of that world, then you would phenomenologically find violation of Bell inequalities.
Yes.
Despite the other level being locally realistic.
Absolutely.
Yes.
Sorry, let me interrupt. You can continue afterwards. I should have stressed that in this theory, any observation that you will make is entirely consistent with what standard quantum theory tells us. So in a sense, I'm sorry for Leibniz principle, but this does not give different predictions or different things that you can observe compared to standard quantum mechanics. Yes, go on.
So my question is exactly about that. So how would you see that you would not also find phenomenological signaling in such a world? Something that looks from the inside like signaling, but is not really.
Well, for this you have to have two answers. One is that you have to follow the math of the entire construction. But the other answer is that since the purpose really was to lift to a noumenal local realistic level exactly what is phenomenally observable in standard quantum mechanics, and in standard quantum mechanics that's non-signaling, that it has to remain non-signaling. So, or perhaps a slightly, maybe more informative answer would be that, remember I told you that this mapping that are called phi from the noumenal to phenomenal states cannot be one-to-one. And that's necessary. That's necessary. If it were one-to-one, then by reversing the arrows, I'm not saying it's right. For all of these things to happen at the noumenal level, it has to be that there are many different ways to obtain the same thing that you could observe. I could explain on the blackboard if I had more time, but
yes, maybe just quickly.
yeah, okay. Let me do something really quickly here. Let's say you start with a phi, let's say a phi plus state. Phi plus is so a superposition of 0, 0, and 1, 1. And let's take that at the noumenal level. Meaning what phi plus really is. Then you could split it. There's phi plus for Alice and Bob. You could split it between the A part and the B part by projecting. And then you could do a negation here. Negation of the first qubit. Only negate on one qubit, because this is Alice. Alice has only one qubit. Alice negates. Now if you negate the first qubit, that becomes 1, 0 plus 0, 1, which is psi plus. So if you put it back together using the joint product, now you get a psi plus. What this proves is that these two states must be different. Because if you had not done this, you would get back the phi plus, which is different. So these two states must be different. But at the phenomenal level, they're the same. In terms of density matrix, these are both completely mixed. So if you were to use the projection, sorry, the phi thing to become phenomenal, these two things would be identical. Whereas these two are not identical. So this proves that that the same phenomenal state can be mapped back to different noumenal states. And that's necessary for a theory like this to work.
Yeah, I mean, I don't want to do this too long now, but I guess the question is a bit different. So I can see, for example, from your two principles, intuitively why you would see a violation of Bell inequality. Because you have basically different versions of the observer.
Yeah.
Now, is there an intuitive way to see why you would not also see signaling in such a world? Or would you really have to go through the mathematical derivation?
Again, we start from a non-signaling theory, which is standard quantum mechanics, and we lift it to the noumenal level.
Yeah.
And this lift will preserve, because it's a morphism, this lift will preserve these properties in particular.
Okay.
So it's automatic.
Then it must be by construction.
Yeah, it's by construction. It's the way we construct a noumenal world,
Okay.
or God did.
Okay.
Bill?
No, it's okay. I'm going to pass.
All right.
Okay, then in front of Bill, you
Who? Sorry. Oh, yeah.
I try to understand what is the noumenal world.
Understand what?
I try to understand what's the noumenal actually state. You said
Yes.
you can take a unitary transformation after you taking out A state and B state separately.
Yes.
And then you take the unitary transformation and you put them together. I don't know if it is possible, and I cannot imagine what's the noumenal state.
Okay.
It's a hypothetical.
No. So all right. Excellent question. So what he says is that he cannot imagine how the noumenal state can be built, which when you project it to the phenomenal level, you get standard quantum mechanics, and yet that the state has a property that you can split and recombine, which quantum mechanics says you can't do, because quantum mechanics standardly is on the phenomenal level. So he can't imagine how it's possible to lift it at a noumenal level, where this, in fact, would be possible to split and recombine. And that's perfectly normal, because the whole point of this work is that it is possible, it's not obvious, and it's how to do it. And I'm not going to go through the entire thing, but and this is all based on information. We have to, in order to do this, we have to define mathematically what is the information that's really there in a state, as opposed to the density matrix, which is not enough. Just the density matrix will not allow us to do what you say, or what I claim, rather. So of course we have to have more information. The noumenal state has to include more information than just the usual density matrix. And what you have to add to the noumenal state for this to be possible is not obvious, but it's not all that complicated. And so this would be, so the noumenal state will be a matrix, just like the density matrix, of the same dimension actually, except that the entries of the matrix would be matrices instead of just complex numbers. And the matrices inside that matrix, so this it's written W instead of M, but just look at it upside down. So the WA here will be the noumenal state of system A. It's a matrix whose ijth entry is given by a rather simple formula, but inside you have something about the local system and something about the rest of the universe to take account of previous interactions. And when you do that, again, there's no point trying to go through the whole thing, but then we can define what's the evolution. I'm just going to zip through the slides to show that it's simple, not trying to explain the detail. So the way that you evolve a state is a rather simple formula. So this is the our definition of evolution of system A, and whereas these are normal, usual unitary operators and matrices. And then we have a theorem. We have the theorem that when you evolve system A under U, you get the same thing as if you evolve a system A under U and the rest of the universe under V. So this is the no signaling. Sorry, this is the locality constraint. So already here we have what we want. I know it's not comprehensible from what I said, but I just want to show it's simple. So this really says that no matter what the rest of the world does on the rest of the universe, no matter what V is, when Alice does U on her part of the universe, on her system, when Alice does U on her system, she gets the same thing as if the rest of the universe did anything they wanted. That's what it says, essentially. So that's the theorem. So that's the statement of the theorem, and the proof is not that long. That's the complete proof. That's it. Again, I won't go through it. It's in the handout. No, it's not in the handout. Of course not. Sorry. The statement is in the handout, not the proof. But it's not such a hard proof at all, right? Or when you split a system, so if at that time we were using trace instead of projection. So think of pi a here instead of trace of b. So if you have a local system, so AB is a composite system, you project onto A. The projection operator is defined that way. Extremely simple. And then we have this theorem that everything works out. And again, the proof is extremely simple.
Sorry.
Yeah. Okay.
Next question is
Yeah.
from what?
Sure.
Sorry.
So this just give you an idea. Next question? Yes?
I want you to comment more on the role of no signaling here.
Yes.
And here's what I'm thinking. This is kind of a vague thought. Suppose I started with a signaling theory.
Yes.
So Alice has some button she can push,
Yes.
and Bob gets a 0 and 1, and when they bring the things together, they find there's a correlation between Alice's pushing and Bob's outcome. With enough cleverness and imagination, could someone lift that, something like that, to a noumenal level and say, look, since the correlations
Well,
don't exist till they come together, there's a
no, sorry.
there's a
Whoa,
local
whoa, whoa.
realistic noumenal thing?
Let me stop you.
Yeah.
When you see signaling, you don't need to wait for to bring the data together to get signaling. A signaling theory is one in which Alice can do something here,
Right.
and Bob knows immediately, no matter how far. There's no need to get together to check
But
that.
no, but signals are correlations, just like the correlations you're not. So why can't I just say, defer Bob's outcome until they come together and say, well, look, there's this correlation. After they come together, we see a correlation between Alice's pushing and Bob's outcome.
Well, I guess the short answer is that we do have this theorem that if any theory which is local realistic, and with this definition, is automatically non-signaling. Therefore, the converse is if it's not non-signaling, if it's signaling, then it cannot be local realistic. Maybe I don't have enough imagination on how I define what it means to be local realistic. But with this definition, it's not possible.
Okay, thanks.
Well,
Sorry,
just to follow up on this, I don't think they actually have to get together. I mean, they can. Alice and Bob can sit down, and Alice can say, "Look, I'm going to signal to you. You go to the other end of the room. What I'm going to do is I'll do something here, and you look at whatever system is, and you will see a change." And Bob will go like outside the room, or however far he has to go, and he sits down, and whoops, he sees the change that Alice told him that she could use.
Right, because if she has a choice, then she can decide in advance what her.
That's what signaling means.
Yes, so they wouldn't have
Yes.
to get together.
Okay.
Thank you.
So, Richard?
Yeah, at one point you said that measurement outcomes never become definite. But at the phenomenal level, when they get together, they agree on what the definite outcomes were.
Yes.
What is it about Alice and Bob in this world that makes that possible?
This is only possible, so the question is, I said that measurement outcomes never become definite, but yet when Alice and Bob meet, they will see these correlations. How's that possible? The answer, at a high level answer, the real answer is follow the math. But a high level intuitive answer is again inspired by Everett. That when I say that there's no definite outcome, it's really because, again, for simplicity, let's take binary outcome. It's because both outcomes are realized. So think of, there are two Alices that have seen the two possible outcomes. They have no conscience of the other. There are also two Bobs. And in the simplest version, in which the two Alices who don't see each other and the two Bobs will just move together to meet, that's when the correlation would appear. That somewhat magically, but the math is magical, each Alice will only see the Bob that she's supposed to talk to.
So whatever Alice and Bob are, they come in multiple versions.
Yes. Yeah, you need that. But you don't need to split the whole universe.
Right.
But again, it's when they meet. So one very nice way to say this is that if you think, let's say, because it's much simpler of the non-local box, of the banana world. Let me just remind you what it is. So we have these Alice and Bob, and well, in banana world, but I'm really going to do it with non-local box. They get inputs x and y, which are binary, and they get out. They put in inputs, they get outputs. The single bits, which are random for the inputs, and the property is that the parity of the outputs is the and of the inputs. So only if both inputs is 1 will the outputs be different, and otherwise the outputs will be the same. And let me skip through these things to go faster. these cannot be used to communicate. These things are non-signaling, and they can be segmented classically 3 times out of 4. Quantum mechanics gives us 85%. And the actual non-local box, or the bananas, do it 100% of the time. Again, let me go through this. Now I can come to your question with this drawing. So Alice and Bob, they have these bananas. And when Alice, you see there's a button here. There's a button 0, 1 on each box. And when Alice and Bob push their buttons, when they push their button, a light comes out, red or green. And if they both push the 1 button, you get 2 different colors. In the 3 other cases, you get the same color. So for instance, Alice gets 1. She pushes the 1 button and it becomes green. And Bob, so Alice gets 1 for Alice, 0 for Bob. So this is one case where he would get same color. And now I really get to the point. When Alice pushes the thing of Bob's thing. When Bob pushes the 0 button, and in this case you will see the green color. When Bob pushes the 0 button, because 0 for Bob means that it cannot be 1, 1 together. Therefore, Bob knows, because he pushed 0, that it's one of the cases where they see the same color. So when Bob pushes the 0 button and sees green, the usual way of saying that is he knows that whenever Alice pushes her button, no matter which it is, she will also see green. And therefore, it seems that Bob knows what color Alice will see when she pushes the button. What Bob doesn't know is that he also saw the other color. In fact, that's not what Bob learns. When Bob pushes the button and sees green, that does not tell him anything about what Alice will see. It tells him about which of the 2 Alices he would interact with later. Because there were 2 Bobs, one saw green, one saw red. And when Alice pushes the button, before or after at the same time, now there are 2 Alices, one green, one red. And the only that the green Bob who pushed 0 can tell is nothing to do with Alice. Nothing to do with what Alice will see. What he can tell is that of the 2 Alices, he will meet the one who saw green. Yeah, and so this is really summarized here. What reversed Alice and Bob. Alice has not predicted anything about what's happening at Bob simultaneously. There's no actual distance. It's only how their lives will meet in the future.
Okay, I think this will be our last question over here.
Okay, so a lot of what you've just been saying has made me think a little differently. But
Speak up, please.
The way you were describing this setup earlier sounds almost like a sort of a flavor of a hidden variables theory, where you have
hidden variables?
You have like a noumenal world where there's what's really going on, and we're only able to access.
Let me interrupt, and then you can continue.
Yeah, sure.
If all there was to it is a more clever way of introducing hidden variables, local hidden variables, if that's all there was to it, then it would have to fail, because Bell's theorem would apply. So it has to be something different. Go ahead.
Okay. All right. So I guess most of my question is just how exactly is it distinct? Is it just the fact that there's no access to these sorts of things? You don't have explicit parameters that you're positing?
That's right. That's correct. Back to Kant. The noumenal state may exist, he said. I would say it does. But it's beyond anything that we can know, in a sense, at least with our senses. This is true. This is true of these noumenal states do have the property that they include information that is completely inaccessible, but it has to be there. Right? We need to add to the phenomenal state. We need to add things which are strictly impossible to access, and that makes the thing work. Now, if you put everything back together, that's called the universe, then you can access these things. But from one system, which is entangled with something else, So from Alice's part of the system, in her noumenal state, there are things that she simply cannot access, even in principle. But it has to be there for the merging to be possible later. Good question.
Okay, well, although the noumenal states might be inaccessible, lunch will be accessible outside. But let's thank Gilles for